Hello, just connecting to NYU right now. Oh. Hi, folks. I'll get started in a moment. All right, let's get started. So on Monday we talked about vtables. So today we're going to move on to talking about another very important aspect of object-oriented programming that's not dynamic dispatch, and that aspect is subtyping. So what is subtyping and how does it differ from inheritance, which we talked about in a lot of detail yesterday? Well, inheritance, we said, was the relationship between implementation. We used inheritance in order to make it possible to reuse code. Oops, let me record on Zoom. Oh yeah, everyone can hear me, right? I see folks are wondering where I was in the chat. Okay, great. Okay, so we said that inheritance was a way of reusing implementation, and it just so happens that in C++, reusing the implementation is very important for actually also letting you, use objects interchangeably, because C++ expects things to actually line up in these situations. So inheritance is all about implementation, and subtyping instead is about the interface the object presents, right? So we're going to think about these objects as like these Smalltalk things where they take messages, and some messages they understand, and the set of messages that an object understands tells us something about what its interface is. And to just harken back to our early example, right? Like in most people would say a color point is a subtype of a point because we subclassed color point from point. Now, whether or not this is actually true or not, that's a difficult question, and that's what we're going to try to elucidate in more detail in today's lecture. So let's try to define what a subtype is. So here is one way to define it. So we could say if the interface A contains all of interface B, and so here we're thinking about the set of messages an object understands, then A is a subtype of B. So why does this make sense intuitively? Well, we were like, hey, if I have a point that supports the APIs for querying what its X and Y coordinate are. Well, with a color point, I still support supporting the coordinates X and Y, and I also support color. But if you just were expecting X and Y, color point will work perfectly well. And so under this definition, we would say A is a subtype of B when it contains all of the interface that B had in question. So color point is a subtype of point. You can mentally replace subtype with subclass, and that would give you sort of in the correct direction. Now, in object-oriented language, in dynamically typed object-oriented languages, there's no such actual relationship, right? Like objects implicitly have an interface in terms of the functions they support, but there's no type system to actually force you to declare that something is a subclass of something else, and you can't pass something into this function unless it is a subclass in this case. So in this particular case, right, like if I have a color point and a point, these might just be objects, right? And they literally only have functions on them, and there's no implicit like need to do inheritance, right? This is also what we often refer to as duck typing, right? As long as it contains enough functions, enough methods, enough support for the messages in question, then the subtyping relationship holds, right? So color point just needs to have X, Y, draw, and color. It doesn't need to also, inherit from point. It doesn't need to have that relationship. Of course, you can, and that makes it easier to implement because when you do have a inheritance relationship, when you do have like a parent class relationship, if you didn't implement the operation in question in color point, it would just get forwarded to the parent class in question, right? And so, one of the like most common places you will see subtyping in language design is when you are thinking about what the collections in your language, like what the container types in your language are. And Smalltalk, when they define their collection hierarchy, they define a bunch of subtyping relationships, right? So the most generic notion of a collection is just something that could be empty and has some size, but you don't really know what else is going on there, right? And then it bifurcates. Index collections are collections that you can access at particular points, whereas sets are not collections. You can't ask what is the fifth element of the set because sets are unordered. So instead you can only add or remove elements from the set. And then, with an index collection, that lets you retrieve an element at some location, but you might also imagine a further addition to the API, which is that you can also put things into the set. And so that's what they call updatable. And what are two updatable collection types? Well, one is arrays, right, which are numerically indexed, and another is dictionaries, which can give you arbitrary keys and will have some sort of hash map. And the one thing that I want to point out again, right, is that subtyping is not inheritance. In fact, in Smalltalk, the way that set was implemented was by inheriting from dictionary, because sets are very similar to dictionaries in the sense that you can implement a set simply by just having a dictionary and then not storing anything interesting inside of the dictionary in question. But even though you might implement it this way, there's not necessarily a subtyping relationship between a set and a dictionary. They just support different operations. So even though this is an inheritance, there's no subtyping in this case. I want to say this over and over again, right? Subtyping is not inheritance. They are not the same thing. They are often the same thing, but they do not have to be the same thing. In C++, subtyping only occurs when you define A to have a public base class B, right? A is a subtype of B if A has a public base class B. So unlike JavaScript, where monkey duck typing was allowed, in C++, if I define a point and a color point, even if they have all the same methods, if there isn't a inheritance relationship, and in particular a public inheritance relationship between them, there's no subtyping relationship. I can't use a color point where a point was expected. That's mostly true because in C++, we can think about using objects as pointers and then calling methods on those pointers. And in that setting, there is no subtyping relationship. But C++ also supports another form of code reuse called templates. And with templates, actually, they're kind of duck typed again. So ha 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 ha. We'll talk about more about that when we get to generics, which is a later lecture. So just to remind you, right? Why does subtyping in C++ only occur when you actually have an inheritance relationship? Well, that's because C++ has a very, very low-level notion of what the interface for an object is, right? So it's not the set of methods on it, is literally the binary layout of the thing in question. And so to actually make sure it's got compatible memory layout, well, you need to actually get inheritance to, get it all done in the situation. And that's the deal with C++. Okay, so I said that if an interface A contains all of interface B, then A is a subtype of B, right? So one of the things that's confusing about this formulation is I said A has to, be bigger than B. So if A has to be bigger than B, then why are we calling it a subtype? Where does this sub come from? Now, of course, you can be like, well, sub is the same as sub in subclass, but if you're thinking about like the interface size, that's kind of weird. And in fact, there's another way we can also talk about subtyping. We could say, if a type A classifies a set of values that is a subset of type B, then A is a subtype of B. Okay? So what does this mean? Well, we can say something like, natural numbers are a subtype of the integers. Why is that true? Well, in any situation, in any function that takes in integers, right, you could also pass in natural numbers. They're just a subset of the valid numbers of integers. So it's also okay to do them in that situation. So that's kind of blah. So actually, I don't recommend using either of these definitions to understand what a subtype is. Instead, we should use this definition, which is that S is a subtype of T if any term of type S can be used asterisk, because what do you mean by used? Well, we'll talk about that. In a context where a term of type T is expected. So I always said things like, hey, natural numbers are a subtype of integers because, if you got a function that takes integers, then you can give it natural numbers as well, because every natural number is an integer, right? So in that sense, there's a subtyping relationship. And when we talked about interfaces, well, the interface had to be bigger because, if you're going to pass in an object to some function and it's going to expect some interface to be available in this situation, well, you need all of you need all of the methods to actually be available, right? If there's some method missing, obviously this isn't going to work. And I just want to explain this slide real quick, right? The bigger, smaller thing actually is fine. Like both of these are simultaneously true, because if you think about the universe of all possible points, right? This includes like normal vanilla points that only have XY coordinates, but it also includes weird points like points that also have annotations, points that like basically any possible subclass of point is inside the global set of points, right? So colored points is just a subset of all possible points in the situation. Okay, so Arthur brings up a very good point, which is naturals can be a subtype of integers, but you can't negate a natural, right? So this is why it's very important to talk about the interface in question. So if the interface required when we're talking about numbers is that we must be able to negate within the domain of the type in the question, then natural numbers are not a subtype of integers. So in fact, it is simultaneously possible for natural numbers to be a subtype of integers and also to not be a subtype of integers, because it depends on the context in which you are using the types in question. And so if you're like a mathematician, then certainly natural numbers aren't interchangeable for integers because, well, they have different properties, right? Integers have extra structure, they have negation, and that's fine. In programming languages terms, we often don't care about this sort of thing, right? Because what I'll do if I pass in a natural number into a function that takes integers is I'll just cast it into an integer and then do the same old thing that I did before, right? And in that situation, like clearly the natural number will always work. I will just negate it like on the inside of the function and get a negative integer, but that was okay because I'm just dealing in integers. And sometimes this is okay, and sometimes this is not okay. And I'm also going to talk about this later in lecture. Great question though. So to put things otherwise, the way that I want to summarize subtyping is that subtyping refers to some sort of like runtime relationship between objects in question, right? It talks about whether or not you can replace something with something else and expect it to work in the context. And often we will have a static type system which will capture this notion, but sort of the subtyping relationship sort of exists independently from the type system. this is a little confusing thing to say because obviously we when we define type systems, we often have to say, okay, our type system supports subtyping, and we are going to define subtyping to work in this way. But all the language's built-in notion of subtyping says is sort of under what situations can you replace an object of type T with some other object of type T prime. And when you're in a language which doesn't have dynamic types, we're talking about a more expansive notion, which is talking about, obviously the type system doesn't tell us anything, but runtime might still tell us something about this. Okay, let me just repeat what I just said with the actual slide in question. So in type system design, when we add subtyping to a programming language, so we've got a programming language with an actual type system, and we want to define what the meaning of subtyping is, we will add a typing rule called the subsumption rule. So what is the subsumption rule? Well, let's harken back to the Curry-Howard lecture where I talked about inference rules, and let's just read out what's going on here. So remember, when we're reading out an inference rule, the bottom of the inference rule says what we can conclude given the hypotheses at the top of the inference rule. So our hypotheses are E has type S, and then if S is a subtype of T, then E also can have type T. So like to go with that integers, natural numbers things, right? If E is a natural number and natural numbers are a subtype of integers, then E also has the type integer, right? So I can so normally, right, when I'm writing a type system, I have a rule which says, like, if I want to call a function, I need to pass in an object that has that type. And with subtyping, I don't have to only pass in objects with that type. I can pass in any object that has a subtype of the type in question. So when you're designing a type system for a language, your job is basically to define what the subtyping relation in your language is. And there's like two problems you have to solve. So one is that you have to make sure that this subtyping relation is sound. So if you're in a language like Java, where your type system is supposed to give guarantees that, for example, you can't segfault a program, you need to make sure that you don't put in rules that like just let you convert willy-nilly, right? Because it wouldn't be right to convert a string into actually I need to think of a good example. You can't convert a string into a number. Well, you can if you're willing to put in an implicit conversion, but that's different from like literally like taking an object that's a string and then like sort of forgetting it's a string and then pretending it's an integer. And that will just not work in most languages. And so, for example, in C++, the way they define the subtyping relationship is they said, okay, if A is a public subclass of B, then A is a subtype of B, and no other situations occur. I'm not going to talk about like the integer conversions. Okay, so so let's try to actually define the subtyping system. I said there was like a few things that type system designer needed to do, and I don't remember where I was going to go with that. But certainly another problem with subtyping is it makes the rest of your type system design pretty difficult. So let's just take a look. I'm setting up my tablet. Give me a moment. Oops, didn't want to do that. Okay, new file. And I am going to switch to tablet. All right. So what I'm going to do now is I said, okay, we're type system designers, and we need to define what the meaning of T1, T2 is. And so what I'm going to do is I'm going to basically present a structural type system that would work for a language like JavaScript, where we're talking about dictionaries, objects, and we're also going to assume that they're immutable. So what's our type? What are the types we're talking about here? So the types we're going to talk about is we're going to have a type of functions, just like we had in Haskell. So really think of this like Haskell, but also with like, sort of records that are a bit more flexible. So you don't have to explicitly declare a data type. You can just give free floating fields. And let's talk about this for a moment. By the way, so just to give an example, right? So if I'm talking about like foo int bar int, right? This type, a valid value of this type would be, for example, foo 1 bar 2. And so if I were given a record of this type, then I could, for example, read out the foo field or read out the bar field, and these would have type int. Okay, any questions about this language that I'm defining on the fly? So my language is going to have functions, and it's going to have these like records, right? So these records are what we're going to call anonymous records, so you don't have to name them explicitly. And the way to think about them is it's kind of like JavaScript. We're not going to have to define any types ahead of time. We'll just we can define them on the fly, and as long as something quacks like a duck, we can use it like a duck. Okay. So I'm not seeing any questions. So let me just go ahead and write my first rule. So my first rule is going to say something like, hey, if I've got one of these record things, then if I want to pass in, for example, if I have a function that is expecting me to provide some record, I ran out of space. Let me clear this out. So if I have a record for which if I have some context where I'm expecting to have a record that contains the fields L1 to Li with types T1 to Ti, then what am I allowed to pass in this case, right? So clearly, anything that I want to pass into a function that expects this, oops, I ran off the, has to also contain L1, T1, fields to Li, Ti fields. But wait, there's more, right? Which is that if it also contains some random extra junk, Lj, Tj, that's okay too. So this is like what often is called the widening, the narrowing rule, which it says that if you've got a record that's got too much stuff, you can drop some of it, forget about it, and you're allowed to use it in that context. There's a question on the chat, which is, can you add or delete fields to the records or append them together? I mean, we're not really talking about that, but sure, we could define operations that let us do that. So for example, to append to records, we could define this to be something like L1. This takes in a record of type L1 to Lj, Li, Ti, and then it takes another function which provides okay, so I need a L prime 1, T1 prime 1 to Lj prime T prime J, and then it would give me the thing that, union this with this, maybe with a side condition that that L1 to Lj Li is disjoint with Li L1 prime to Lj prime. Right? Some rule like that. Hypothetically. It's not really so the design of this sort of type system is what's called row typing, and it's not too relevant to our question on subtyping here, but like, you know, if you're curious about this kind of typing rule, that this is the keyword you'd want to go to. I hope you can see everything here. Okay, I'm going to delete this. Okay, so returning back to this example, right? So if we're in a context where we want to pass in a record, we can pass in a record with more fields, and that's okay, right? There's a subtyping relationship there, which says that if you have more stuff than you need, you can get rid of it and you know, pass it in that situation. Okay, another rule is just the so-called depth subtyping rule, and that just says that, well, if T1 is a subtype of T1 prime, and then T2 is a subtype of T2 prime, all the way up to Ti is a subtype of Ti prime, then if I've got some record that's, you know, L1 T1 all the way up to Li Ti, then this is a subtype of L1 T1 prime all the way up to Li Ti prime. Right? So all I've done is I've kept the fields the same, but I just said that the thing that I'm storing in every field has to be a subtype of the thing I'm storing in the same spot on the record in question. So in other words, right, if I've got a record full of natural numbers and I've got another record full of integers, right, like that, there is a subtyping relationship here if the fields are all the same. Now I can also combine these two, right? So I can forget about the stuff that I don't need and also you know, do subtype replacements for the things on the inside. Okay, so hopefully these two rules are relatively intuitive. You can discard stuff you don't need, and the subtyping rule, you know, on the inside, it applies on the outside. Now, an interesting problem is the subtyping rule for functions. So in the subtyping rule for functions, we ask the question, under what situation is a function a subtype of another function? So when can I use T1 arrow T1 arrow T2 in the context where T1 prime arrow T2 prime is expected? So let's think about this a little. And let's think about what the output is, right? So functions are very similar to regular old values if they don't take any arguments, right? So if I got a function that doesn't take any object arguments, like say a dictionary in this case, and I you know, return t, this is basically the same thing as saying t. So when I've got a function and it returns t2 primes, or it returns t2s, in a context where I was expecting t2 primes, all I need is to be able to reuse t2 as t2 primes in that situation. So t2 is a subtype of t2 prime, then T1 arrow T2 is a subtype of T1 arrow T2 prime. So if this is making your head spin, we can be a little more syntactic and we can say, hey, you know, this subtyping, right, goes from T2 to T2 prime, and the rule for T2 prime does the same thing, right? The arrows go the same way. What about T1. Is this, are we just going to do the same thing and do, there we go. Are we just going to write this down to finish off our subtyping rule? Any thoughts? So to answer this question, I want to return to my slides briefly and talk about what this means. So let's do a concrete example because it's easier to think about these if we're not like just thinking about, oh, you know, these function types, well, what's going on. So I'm going to imagine this situation where I've got some tomatoes and I've got some vegetables, right? So tomatoes are, well, okay, technically tomatoes are not a vegetable. Culinarily, they are. So we'll just think about a context where we're just talking about what kind of recipes we can cook, right? So tomatoes are a subtype of vegetables because you know, they are a vegetable. So anytime you are asking for a vegetable in, you know, generically, a tomato will satisfy the bill. So we've got this subtyping relationship right here. Okay. So if we want to talk about functions, then what we're talking about is we can think of these as sort of like processes or like recipes, right? So a function from tomatoes to tomato soup is some operation that someone said that's the wrong way around. Was that in reference to the whiteboard? It is the wrong way around. Okay, I want to keep going. I hope I didn't make a mistake. So we can think of functions as recipes. So we've got a tomato recipe. So this tomato soup recipe says, give me a tomato, and then I will give you some soup. And we can also have a vegetable soup recipe, which says, give me any sort of vegetable, and then I will give you the soup. This analogy is a little creaky, but like imagine this like hypothetical recipe where it's like generic vegetable soup, right? Like I can make cucumber soup with this, I can make carrot soup with this, I can make tomato soup with this. Just give me some vegetable, and I'll tell you how to soupify it. So you know, this is kind of super powered recipe. So what I want to say is that the vegetable recipe is a subtype of the tomato recipe. That is to say, in any situation where you needed a tomato soup recipe, you can use the vegetable soup recipe instead. And to understand why that's the case, let's imagine that you know, you're calling your friend and you've got some tomatoes in the house, and you need a recipe for them. So you call up your friend and you're like, hey, I need a recipe for how does the story go? I messed up. Okay, so it's the other way around. Okay, so your friend calls you on the phone and they're like, yo, I've got some vegetables at home. Can you give me a recipe for how to go about cooking them? And you're like, oh, you know, what kind of vegetables, right? Like, you know, maybe you have tomatoes, maybe you have cucumbers. Please tell me, you know, what kind of vegetable you have. And they say, that's not important. Just give me a recipe I can use, right? I can't give them a tomato soup recipe because if I give them a tomato soup recipe, they might not actually have tomatoes. So the tomato soup recipe is not usable necessarily in this situation. Now, if I have one of these like wonder recipes, vegetable soup recipes, which just say, hey, no matter what, this recipe will work. No matter what your vegetable you give it, it'll give you out soup. I can give my friend that recipe, and that recipe will work in that situation. So heading back to the slide a moment. So this is wrong, right? So if I had tomatoes and vegetables, then when I have them as the argument, I need to flip it around. So symbolically, for T1 arrow T2 to be a subtype of T1 prime arrow T2 prime, T1 prime must be a subtype of T1. And this like flipping of the subtype arrow is so famous that we even gave it a name. So this is what we call is in the I'm blanking on the name. So when we are talking about the return type of the function in question, that refers to the covariant position of a function. And what I mean by covariant is that if T2 is a subtype of T2 prime, then a function that returns T2 is a subtype of a function that returns T2 prime, right? Like the relationship is the same. When the relationship flips, which is the case for arguments of functions, then we call this being in contravariant position. So a function argument, we require T1 prime to be a subtype of T1 so that T1 arrow T2 is a subtype of T1 prime arrow T2 prime. And so this is the correct rule for function subtyping. So going back to the VM for a moment, the slides a moment. Let me dump my tablet. If I have a recipe for soup, right? Then a recipe that is willing to take more arguments, more possibilities than a recipe that is very specialized, it's only taking one particular type of thing. That recipe is usable in more situations. The vegetable soup recipe, the super generic vegetable soup recipe, is more usable than the tomato soup recipe. So we can even do a little more crazy situation. So let's think about this situation. So I've got a function which takes in tomatoes, a function of tomatoes to soup, and gives me a soup in that case. And then I've got another function that takes in a function of vegetables to soup and produces a soup. And we have some question, which is, what is the subtyping relationship between these two functions? And to help sort of intuitively understand how this situation works, let's return to our situation with the friend who called us on the phone asking us for a recipe. So we've got one friend asking us for a recipe. The story so far is we had a friend, they called and asked us for a recipe, and they were like, yeah, I have no idea what vegetables I have. Can you give me a generic recipe that'll work no matter what? And I couldn't give them the tomato soup recipe, right? Because it wasn't general enough. It didn't work in enough situations. And if I had some other friend who called me and said, hey, Ed, I've got some tomatoes at home. Can you, give me a recipe that I can use to turn these into soup? This is a much more reasonable friend. They have actually told me what the heck the vegetables they have at home are. And if I had a tomato soup recipe, I could give them that recipe. And if they had if I had a generic vegetable soup recipe, I could also give them that recipe in that case. And so these people asking me for recipes correspond to these higher order functions that take in a function. So sort of intuitively, because the tomato soup recipe asking for friend is a lot more reasonable than the I have no idea what my vegetables are friend, there is a subtyping relationship, which is I would much rather, like in any situation where I'm prepared to deal with my vegetable soup recipe asking for friend, I can also handle it with my tomato soup asking for friend. So just to recap, right? We said tomatoes are a subtype of vegetables, but vegetable soup recipes are a subtype of tomato soup recipes, but tomato soup recipes to soup are a subtype of vegetable soup recipes to soup. So one reason why it's kind of nice to have, okay, so I've presented two ways to think about like how to think about function subtyping, right? So I wrote down a rule using very abstract syntax on the whiteboard saying, hey, like this is the arrow relationship and this is how to go. And I also did this very long and convoluted story where, you sort of just thought morally about like what the situation was going on. And once you like were able to come up with some approximation for the function in question, it became clear that one of these was okay and the other one wasn't. So which of these is better? Well, like, I think if you're trying to build intuition, it's easier to like think about the story, to think about the particularities of the situation, the actual concrete situation, and work it out that way. Because it kind of makes sense, like when you couch it in real world terms. But if you need to do it fast, right? Like you got this thing and you need to figure it out ASAP, you probably just want to rely on the symbolic approach and like, keep doing the flipping until you get it to the right place. So it's two different ways to do it, right? One slow but intuitive way and another that's fast and uses formalism. And one of the reasons we use formalism, and one of the reasons why you might want to practice formalism until it feels like second nature, is so that the formalism becomes the intuition and you don't have to like reason out a very long story about tomatoes and vegetables from scratch. All right. I don't feel like I explained this very well, so I'm going to pause a moment to see if there's any questions. So the important thing to remember is that function returns are covariant, so they preserve the subtyping relation, but function arguments are contravariant, so they flip the subtyping relation. Okay. Let's talk a little bit about what this means in the real world. So, one question that you might wonder about is, okay, I had these dictionaries and I had these functions and like how the heck, like that's cool and everything, but Ed, like in my real programs, I have these object-oriented programs with methods, and these methods have signatures. How the heck do I actually do it in this case? And so what we can do is we can actually model objects inside of our little language of records. Although I do have to add one more language feature, which I will do right now. So let's say we have this class and it's named A and it contains two methods, bool equals A. So basically it says, hey, give me another A and then I'll tell you if they're equal. And maybe it's got another function clone, which you can call to get out a fresh A star pointer. So if we, sort of squint our eyes and we try to convert this into records, well, we said that in JavaScript, methods are basically just function valued values on the record. So we could say, okay, well, this is just a record, and equals is some function that takes in an A and produces a bool, and clone is just some function which doesn't take in anything and produces an A. But there's one caveat, right? Which is that this A needs to be this class A. And so the way that like you would model this if you were writing a completely structural type system is you might introduce, say, a recursive type where you're saying, hey, you can pass this in as long as it is some type that is got this thing, right? Like as in the equality test requires you to pass in an A that itself supports equals and clone. So this little mu operator just says that, well, A represents this record that has two fields and has these two functions, and those functions, once again, recursively support A. So it's like a sort of infinite type in question for this situation. By the way, how do we check if one of these infinite types is a subtype of some other type? And the rule is a little subtle, but it basically just says that suppose that A is a subtype of B. Then if I take equals and clone, and I check if equals A arrow bool clone unit arrow A is a subtype of equals b arrow bool clone unit arrow b, if that subtyping relationship holds under the assumption that A is a subtype of B, then this entire recursive mumbo jumbo is a subtype of the other thing, where we have A versus B. And why is that? Why does the rule work this way? Well, it's because that because there's this recursive situation, it's not enough to just check if these things are subtypes of each other. We also have to make sure things are being used consistently in this case. So here's a pretty interesting situation, which is that let's suppose that we have a class B and it subclass is A, and we for example want to sort of change the signature a little bit, because we're like, hey, when I clone an object like this, I want to return an actual honest to goodness B, right? I don't want to return an A, because if I've actually got a B in hand, I want to remember that cloning a B object actually gives me a B in this situation. And is this okay? And we can figure this out by applying the rules that we've done in question. But we can also think about this intuitively, which is that if I've got one of these clone methods and it's returning a B, then that clone implementation is perfectly acceptable for what A expected. A was expecting clone to return an A. So we said, okay, I'm going to return a B instead. B is a subtype of A. So in the context where I don't know that it's a B and I just know that it's an A, if clone returns a B, that's okay, because B is a subtype of A and can be used anywhere A is expected. So this feature is called return covariance. It says that when you subclass a class, you can replace the implementations of methods with implementations that return a subtype instead. And both C++ and Java allow this. We can also check symbolically that this is okay. And the way we do it is, okay, back to the whiteboard for a moment. So the way we check this is, okay, so the question in hand is, if I have A and it contains some method f which goes from A to bool, and I have method G which goes from unit to A, and I want to know if this is a subtype of B, let's forget about this method for a moment. It's not really relevant. So what did I say the rule for this case was? The rule for this case is that if I want to show that these have a subtype relationship, assume that A is a subtype of B, and then show that GA is a subtype of G arrow B. I've got some stuff I need to erase, so let me just erase that. Okay, and so how do I show this subtyping relationship holds? Well, I've got two records. They've got the same fields. So this rule says to show that two records have the same, two records are subtypes of each other, I only need to show that their field labels are the same. They are. They're both G. And that the fields themselves, I'm running out of space. That the field types themselves are subtypes of each other. Okay? So now we got functions. And what we said with functions is that when we have two functions, we need to check that the return types are subtypes and the argument types are just they're swapped. Although in this case the argument types are the same, so there's no problem. And then this is vacuously true because every type is a subtype of itself. I didn't add that rule, but that's also a rule. And this rule is true by assumption because we said we get to assume that A is a subtype of B. So we're good, and the subtyping relation holds in this situation. So the other situation, though, is what if I instead try to replace the argument to equals with B? So what's going on here? So sometimes when you're defining a class and you're subclassing from it, you want to define equality on the subclass. And you might very reasonably want to say, okay, well, give me a B, and then I'll test if it's equal to B. And this is wrong. This doesn't work, right? Why doesn't it work? Intuitively, the reason it doesn't work is because this class B needs to work in any situation A is acceptable, right? And so A can have the method equals called with an argument that's A. But B, well, that's not an A. The implementation of equals for B is expecting a B. So there could be A's out there that are not valid B's because B is the subtype of A, not the other way around. So clearly this implementation is not good enough. If you try to compare a B with just a plain old A, this implementation would not be callable in this situation because you have an A and not a B. And you can't convert an A into a B. We can also work out that this goes wrong when we do it symbolically. So we'll do the same thing. So back to the tablet for a moment. We'll do the same thing, but this time it'll be A arrow unit, B arrow unit, and then we'll have A arrow unit as a subtype of B arrow unit. But then we'll have a problem because the contravariance rule says we must prove that B is a subtype of A, but we don't get to assume that. We only get to assume that A is a subtype of B, so the computation doesn't go through. Here's another situation that's pretty interesting. So in this situation, we've got two classes, A and B, and A defines a function f, and in Java, you can say explicitly what exceptions a function might throw. So this class A says f could throw an IO exception, or it could throw an index out of bounds exception. And one question you might ask is, when I override f in the subclass B, am I allowed to remove some of the exceptions from the exception throws list? And once again, if we reason about this, the answer is yes, because the contexts where A calls F are prepared to handle IO exceptions and index out of bound exceptions. So if you just don't raise the index out of bounds exception, that's fine, right? Because it's got the handler, but it doesn't need it to happen. So another way to think about this is, checked exception annotations are some form of talking about what the return type of a function is. And so there's a rule that I didn't put down on the slide, but there's a rule for variants, which are basically it could be X or it could be Y or it could be C. And the variant subtyping rule simply says that, if you have a function that returns less things than another, that function is a subtype of the other because, there's a smaller set of possibilities and that induces a subtype relationship. Okay, so I want to preface the lecture on generics by talking about a kind of interesting subtyping fiasco that showed up in Java. So in Java, there is this thing called an array type. So an array type in Java says that given any type, you can put two square brackets on it, and that gives you an array. So S is a single object, then S open square bracket, close square bracket is a array of S's. And then Java sort of very blithely decided they were going to add a subtyping rule. And the subtyping rule they added was that if S is a subtype of T, then arrays of S are a subtype of arrays of T. Now, this kind of seems reasonable until you dig into it some more and you find out that actually this rule is wrong, it's broken, it's unsound. So here's some code that breaks it. So imagine that you have a class A and you have class B that extends A. Let's create an array of B's. So this array, is just, we've got this B array and it's got a bunch of B's in it, right? So we expect it to only have B's. We don't expect it to have A's. The array subtyping rule says that if I have a B array, I also have an A array. I'm allowed to do that type conversion to get out an A array that is pointing to the same B array. And now I can break it. I can break it simply by using my A array to put an A, not a B, an A, into the array in question. And now when I look at it again from the B array perspective, well, I'm expecting everything in it to be B's, but there's an A, and I've broken it. And so you will in fact get you'll get an error in this case that isn't caught by the type system. The way that Ken Shan liked to put it is that if I have a bowl of bananas, I can't turn it into a bowl of fruit. I can't cast it into a bowl of fruit and then put an apple in it, because now I'll have a bowl of bananas that has an apple in it. It just doesn't mean anything. It's not the right semantics. Java did this by accident. They didn't realize they had messed it up until it was too late to change. But there was it's not that recent, but there was a funny fiasco with the Dart programming language where they basically they had subtyping and they needed a rule for arrays, and they decided, we'll just make them covariant. And people got very, very angry because, come on, we already know that this is not allowed. And another way to figure out that there's a problem here is to think about what the interface for arrays is. So what is an array, right? So an array, we can obviously get out elements from the array. So when we get things out from the array, the element of the array is in covariant position. It's the return type of the function. But we also support putting elements into the array. So that's put, right, which takes an index and an element and then puts it into the array. And because there's a reference to the type in the covariant position as well as in the contravariant position, there's no subtyping rule that applies for arrays, right? Like if you have a bowl of bananas and you have a bowl of fruit, they're just not interchangeable with each other in any sense. By the way, if you don't recall, but a long, long time ago, we were doing the lecture on monads in Haskell, and I showed you how to break Haskell's type system using unsafe perform IO. And in fact, this is actually the same idea on how we broke it. We manufactured this polymorphic IO ref that, polymorphism is a form of subtyping, right? Like if I have a value of type A, where undefined, I can use it anywhere. Like if I need an int, if I need a bool, anywhere. And so Haskell, just lets you do that conversion. But if there's, if you can both get and put, like is the case with IORef, that's unsound. Any questions so far? There's a question which is, the problem is in a way that it's the same array. Couldn't you technically say that when you cast you have to copy or something like that? And the answer is yes, absolutely. So you have immutable arrays or arrays you can't actually modify, then covariance is sound. And we're actually going to talk about some other ways to solve the problem when we get to generics. Okay, so let's talk a little bit about subtyping and beyond. So this discussion that we've had so far has been all about hey, I'm writing this type system, and I need to like sort of figure out if something should be allowed or not, right? And we looked at all these examples of like Java language designers being like, is it okay if when I subclass a class, they return a subtype of the return type? And the answer is yes, that's okay, no problem. But there's more to life than just, does my program type check, right? We might actually be interested in, what does my program mean, right? Just because my program type checks doesn't mean it's actually meaningful. And so Barbara Liskov proposed this concept of behavioral subtyping, where she said, hey, when we talk about subtyping, it's not just about whether or not it type checks or not, or whether or not it doesn't throw errors or not. But in fact, what we should be looking at is properties provable about the objects in general, right? So this is like kind of similar to like that discussion we had about natural numbers and integers, right? You can't negate in natural numbers. So in that sense, there's no subtyping relation there. So we need to think about like, what are all the things we could possibly say about these objects? And then if these things are true, no matter what object I have X of type T, then when I want to have a subtype, that property should also be true no matter what the objects in question are. And so if I'm just talking about like just structurally like how things are put up, the rules I gave are perfectly acceptable. But sometimes when we define objects, we have higher level invariance. We have more properties, more implicit structure that we're expecting out of our objects, and this can cause interesting behavior. So we already talked about the very degenerate case, which is we have cowboys and pictures, right? And just because they have the same method, right, draw, doesn't mean they're actually subtypes, because they just do completely different things. There's a comment in the chat, which is, well, there could be a relation in the other direction. I think this is in relation to natural numbers and integers. Anything you can do with a natural, you can do with an integer. That is not necessarily true, right? It depends on like what context you're working in, what operations you're demanding out of the things in question, right? Like if you are demanding that it's representable, If you're demanding that it's representable without using a negative sign, well, that's true for natural numbers, and that's not true for integers. So here's another example. This one comes from Oleg Kozelyov, and it's talking about bags and sets. So a bag in collection parlance is an unordered collection of possibly duplicate items. So they're like sets, but instead of only ever having one element of anything, you can have as many as you want, right? So it could be, you could have like 5 copies of 2 inside of a bag. So yeah, so a set is a bag with no duplicates. So when I say something like a set is a bag with no duplicates, often people will be like, oh, maybe there's an inheritance relationship here. I can just define a set as just a bag with the no duplicates invariant. And so like I can try doing this in C++. And if I do this in C++, what's going to happen? Well, I inherit from bag, and then I just, need to say, okay, well, if I put things into the bag, put things into a set, I just need to not put it into the set again if it's already a member in that case, right? And then I might have some test, which is testing properties about bags. And I might say something like, hey, so if I got 3 bags, then if I union the bags A and B together, then if I test if, and then I might, this function, sorry, this is not a test. This is like a function that returns a property. So I'm testing essentially whether or not the union of the bags A and B is contained within C. Okay? So this is a function, and another way I might try to write this function is I could say, instead of like allocating a clone of A, I could allocate a fresh bag on the heap, add A to it, add B to it, and then test if this relation holds. But if you do that, then you will actually end up with differing behavior depending on which implementation you did when you try to use this function on sets. So let's just briefly see why this is the case. So in the first case, what we did was we said, okay, clone the bag. So that gives me another set. So when I pass in a set A as an argument, that gives me another set. And then when I add the set here, what that does is it just says, okay, I'm just going to go ahead and try to add one to the bag AB. But there's already one there, so I don't add it. So I just have a single one. And now when I do the inclusion test, I see, okay, there's 1, 1 in this bag, and there's 1, 1 in the other bag. So hooray, this is true. And I get true in this case. But when I allocate a local bag, if I pass in a C set as an argument, I'm still allocating a regular old bag here. And so when I do A and B, I actually will add 1 multiple times. And then I end up with a bag that has 1 twice. And then when I do the normal bag comparison operation, well, if I have, AB with 1, 1 2 times, that's certainly not included in a bag that only has 1 once. And so it returns false. So why is this a problem? So the details of the example are not that important, but like at a high level, what's gone on is we did a seemingly innocuous transformation, the inner code. We just did a refactor that looked perfectly reasonable, but suddenly changed the behavior in a substantive way for our use of the subtype. In this case, we tried to have set be a subtype of CBag. And so the Liskov substitution principle says that, hey, sets should not be a subtype of bags because sets don't have the same set of properties that are upheld by bags, right? Like if I put a element into the bag twice and then I ask how many times is that element in the bag, I expect to have seen it put in 2 times. But my modified implementation of set only adds it in, well, possibly 0 times because it was already in the set in question. And so like this property, this condition, this post condition gets violated by the implementation of CSET. So we've got all the same interface, right? We've got all the same methods. They don't even raise errors, but I can't do a subtyping relationship because it is semantically not meaningful in this situation. So yeah, if you're going to do this, don't make it a public inheritance class. And so there's a like moral to the story, which is sort of like a general guidance when you're writing object-oriented code, which is that when you are like writing code and you're using inheritance just because you want to reuse code from some other context, that's fine. You can use inheritance to do that. But usually you're not going to have any sort of behavioral subtyping relationship here. Unless you are like you really are like there's very, very abstract interface, which doesn't give many guarantees at all. And that's the situation where subtyping is more likely to happen. So it's like subclassing doesn't even really like, it does give you a subtyping relationship, but most of the time it isn't actually a real subtyping relationship. The places you're going to get those are with interfaces where there's a very abstract notion of what an object is supposed to do. And of course, like this stuff would have been less of a problem if, we didn't have mutation and we didn't let you override stuff, right? So if you're immutable and you can't override behavior, then like behavioral self-typing will basically work most of the time. But it's not really object-oriented programming at that point. Okay, so that's all the slides I had for today. Here's a recap of the Blackboard. So if you wanted to like go take a look at it, you'll be able to find it in slides. Any last questions before we wrap up for today? Okay, well, there is a question. Okay, so question from Twitch, which is, do interfaces guarantee a subtyping relationship? No, that's not exactly what I mean. So the difference here is, okay, so in the definition of Liskov substitution principle, we've got this like phi thing that says, you know, the set of properties which are provable about objects of type T. And when you talk about a concrete class that like actually has an implementation, there's actually a lot of behavior you can observe from it, because like it's real, like it's honest goodness living breathing object that has concrete implementations for everything. And then like you know the aphorism that like, you know, any observable behavior will become part of the public API contract. It's kind of like one of those situations here. So you can't just substitute in some other implementation and expect it to work unless like everything that the original thing did was exactly the same. So in practice, this is like kind of impossible to do, and people don't actually like abide by the list-call substitution principle when they're writing real code. Instead, what they do is they say, okay, yes, it is true that like there is a very detailed, specific behavior for this object, but that's not what I meant when I wanted to talk about this being a type, right? I actually have some more abstract idea where like this class, you know, has some properties, but not all of the ones you can actually observe from this particular one. And interfaces are a great example of this, right? Because an interface doesn't actually have an implementation. It just has a bunch of methods and like some documentation saying what the methods are supposed to do. And then it's a lot easier to implement things that abide by that specification because it's not uselessly detailed, and like it actually gives you wiggle room to do interestingly different things. That's the answer. All right. Well, thanks everyone for coming, and I'll see you all next week.